Once you're done with that, please let me know.
Yeah, I managed to upload it. It says DBA intro to NN dash NN versus LLM capabilities.
Uh, what is it?
Now I uploaded it.
Yeah, lab underscore one underscore and then forest data set, right?
Yes.
Okay. The file is well annotated. So please go through the file and try and understand what we are trying to. We're not really trying to, what to say, achieve anything in this file. The file is designed in such a way that you are able to see what happens when we turn each knob, so as to say. Like what happens when you change the activation function, what happens when you change the optimizer learning rate. So that's basically the goal of this notebook. All right. So go through the file and see what you can understand. First, let's start with the data set. So look at the data set and just tell me what you understand from the data set. What is the goal? Um, or what are the columns?
It is a forest coverage data set.
Okay.
It has columns like elevation and aspect, slope, and
Okay.
horizontal distance to hydrology and vertical distance to hydrology,
Mm-hmm.
and horizontal distance from the roadways.
Yeah.
Keel shade, how much it is at 9 a.m., noon, and 3 p.m. And
Mm-hmm.
horizontal distance to fire points is also there. And the wilderness area, there are four different parameters, area 0, 1, 2, 3. And it has a lot of soil type parameters, like it looks like
Okay.
a one hot parameter. And there are 40 different types. And there is a cover type, which is a integer data type.
Okay. Mm, okay. So someone else, what are we trying to predict here?
Sorry, Professor. I think at my end, I'm seeing something completely different. Is it okay if I share my screen?
Yeah, sure. Go ahead.
Let me know when you can see my screen. I'm seeing something like this.
Yeah, this is correct. Okay, that's probably because you haven't run the cells. That's why there is no output.
What do I need to do?
Okay. So you see the little plus the play button next to a cell. Just click on that and the cell will run.
Oh, okay.
So for how many of you this is the absolute first time trying to um, use the Google Colab?
Yeah, first time here.
First time here as well, Arthur.
Yeah,
Yeah.
first time here for me.
Great, okay. I'm sorry about that.
First
Okay.
time.
Okay, sure, no problem. So let's start from the beginning then. You can stop sharing your screen.
Yeah, okay. Oops. Yeah.
Okay, so we are going to start with so this is your Google Colab. It's one of the easiest coding tools available, and I've set the whole lab in such a way that you don't have to really do any coding. What is expected is really to change some of the numbers that we would find here. So if you come to this cell, I have some parameters here where I hope you are able to reach this cell. Don't worry about the the output of each of these cells. That's okay if we see different things. That's fine. If you come to this cell, you'll see things like number of hidden layers, number of neurons per hidden layer, the hidden layers activation function. Should we want to use batch normalization or not? What is the dropout rate that we want to use? What is the regularizer? Um, what is the regularizer value? The kernel initializer. These are terms that we have learned when during our basic neural network session. What optimizer we want to use? It takes three options. SGD. SGD is basically gradient descent, stochastic gradient descent, Adam optimizer, and RMS prop. Then we have learning rate. Should you implement learning rate decay or not? The decay steps, all these are there. And then momentum. This is the stochastic gradient descent with momentum initialized. And then there is a batch size as well, a number of epochs, and a validation split, train validation split. So these are the hyperparameters that we can actually control. And based on these parameters, hyperparameters, it is going to initialize the neural network and it is going to train it. Um, okay, so this is the architecture and this is how the training looks. This is what the training would look like once you start running it. Don't worry for now. And our goal is to just follow or trace the training accuracy, the validation accuracy, see, find evidences of overfitting, underfitting, and all that. Okay. And we have different kinds of experiment here, where we can just play around with these numbers and we'll see how far we can go in this uh, collab notebook. Okay. So this collab notebook has two types of stuff. So one that is normal English, um, where you type anything here and it will be treated as what's called markdown. It won't be considered as code. Okay, and then there is um, another type called code cell. Okay. Okay, so the whole notebook is made up of, as you can see, multiple such boxes, right? Each box is going to be called a cell, right? Each box is a cell, and there are two types of cells, a markdown cell and a code cell. A markdown cell is like just English text. It is where you want to write your comments, right? Want to write anything about the data set and or like your workflow and all that. Anything that's normal English, you write it as a markdown cell. Anything that you want to be executed as a code, you would write it as a code cell. So you see the difference in font between this and this. This is a markdown cell. If you double click on it, you'll get something like this, where here is where I will type elevation and elevation 1, and you can see whatever I type. This is what it would appear as. Okay. Um, let's not worry too much about this. So Markdown is basically English, and it would consider, it would expect formatting kind of syntax. Like for example, a single hash means the font is going to be big. These asterisks, they mean that it's going to be bold. A triple asterisk means that the font size is going to be smaller, and four asterisks means that it's going to be like normal size, right? So all these are formatting things which you can do in the markdown type of the cell. You will get this if you double click on a particular cell, right? Uh, and then there are the code cells. The code cells would expect Python syntax. Okay. So it has to be Python code for it to run properly. And for running a cell, we just need to do shift and enter. That would actually run the cell, right? Or you can click on this little play button next to the cell, and that would run the cell. I think it says control enter, but that's okay. You can do control enter or shift enter, and that would basically run the cell. Click on press control, and while pressing control, press enter. Okay, try to run a couple of cells now, and let us see what happens.
Can you see those tables that you could see at your end?
You can't see it or you can see it.
No, we cannot. I cannot see it. I can
Okay.
share my screen. Yeah. So when I run this, this is run, but there is nothing like a. Okay. Do not load the JavaScript files here to display. Say some third-party cookies are not allowed by your
Just
browser.
reload this page. You are logged in, right?
Yeah, I'm logged in. Oh, okay, I can see that now. Yeah. Okay, I'll stop sharing. Thank you.
So see if you are able to run the cells. Once you confirm, I can.
What are we expecting to happen when we run it?
Okay, so when you run it, you will see something like what he showed there, like some tables. You would expect to see something like this. If you run cells 1, 2, and 3, you will see something like this. So if you're able to see this, I think you're good. Let's run until that.
Professor, when I trying to open that file, this
Mhm.
already has the table out there.
Yeah, it is saved from my run. Um,
So I just to rerun, right?
yes, you can. You should probably rerun. Yeah.
Thank you.
Professor, I'm getting an error.
See the screen. Yeah. I think you can share your screen.
Can you see it?
Okay. Okay. So this is forbidden. Okay. Did you run the first cell?
Mm, I just saw the run icon and I just ran it.
So if you see the little green tick mark, it means that it ran correctly.
Oh, I was saying HTTP error, explain error. So that's one. Where is it? Oh, this one. This is the.
No. So the little tick mark is right under one, the previous cell. Left
there.
corner. Yeah, yeah. That means that the previous cell ran properly, correctly. So the little tick mark says that, and I'm not sure what's happening here. It's really too small. Forbidden. Anyone else getting this error?
Yeah, we have to include that matplotlib, professor. Matplotlib, import matplotlib as PLT. That is missed, so it can be added in the top and then it goes off.
No, this is not a matplotlib, right? I don't think we are
Oh,
not
okay, okay.
using a
Sorry, sorry,
matplotlib.
sorry. Yeah, yeah. No, this was going through smoothly, professor. It was taking time, but it was happening.
Mhm.
It's
Maybe.
an HTTP error, so it means it cannot connect to the resources
No,
outside resources.
this could be your firewall is blocking this particular port. Are you
Yes,
on
the
a RP?
forbidden.
Yeah, yeah.
So it must be blocked somewhere in the firewall.
Are
Yeah,
you
yeah.
using an office laptop or anything?
No, it's my personal one.
Okay, the best place to start would be to open ChatGPT and paste this error there and basically ask what's going on. Paste the code and also the error that you got along with that. Yeah,
So there is a 403 forbidden, right? So it
yeah,
means
correct.
the port is getting blocked.
Yeah, probably how to fix that also.
Okay, I'll stop sharing and check it out
Yeah,
quickly.
yeah. Anyone else got any error?
Yes.
Yeah.
Only thing is, like I was finding that the PLT was not imported, so that I could resolve, and it went up to end, professor, without any issues.
Okay.
I can't see number 4, and then it jumps from 3 to 5.
Yeah, actually, I see that PLT is not that correct. But how did it run for me then? PLT dot show.
I
Dot
mean,
win.
that must have got deleted. I mean,
Deleted, yeah, probably, yes.
My professor's giving me a pretty long explanation, but seems to suggest that, as was mentioned, there's a firewall. The data can't be accessed, but that's strange because shouldn't be any firewall. So,
It could be a geographic limitation also, Atif.
meaning,
Whether that dataset accessibility from the region from where you are accessing.
Leon, you are in the same city as I am. Were you able to run it?
You're in Vancouver, right, Atif?
No, I cannot get in.
Nias, can you give the uh, matplotlib SPLT in the chat box, please, for everyone?
Will do. Will. Sure.
Atif, try to refresh your whole browser, see if it works. Okay. Yeah, I think because we are all first-time users, so it's taking some time because there is some run that is happening in the background is what I'm observing right now.
Would prefer to if you have any other browser, maybe you can try with that as well because it looked like that your request is going to the server, but it is not getting rendered on your browser. So maybe you can try it with another browser as well. If you
Okay.
have a Firefox or Internet Explorer, maybe you can try it. Yeah, try Explorer.
Yeah. Yeah, I'll do that. And Professor, you were asking something from Niaz. What is that supposed to do?
It is
Yeah.
one line what you need to add at the start of the code. I'm just pasting it. Just give me a moment.
So are you doing matplotlib.pyplot or just matplotlib?
Just matplotlib.pyplot.
Yeah, that's it.
Only thing is I was doing it on some other machine for this one. So
No, I'll do that. It's okay.
yeah.
It's okay.
Professor,
So I've given a line of code in the chat box. Just paste it here. Paste it here in the first cell as the last line and rerun the first cell. Okay, once you are done with this, you should be able to run the next cell, which basically shows the number of samples for each of the forest type. So the data set is basically, as Niaz explained, it tries to predict the forest type or no, the cover type, the forest cover type, by using the different soils, by using different other, parameters like the shade and distance to roadways, hydrology, slope, aspect, elevation, and all that. We are trying to find if we can find the type of forest cover. Like I'm not sure, there are different types of forest, right? Different types of trees and all that. So we're trying to predict that by using these parameters. And this plot basically gives us what each sample is supposed to be. How many samples are there in each class? Okay, and you will basically notice that there is a huge class imbalance here. Forest types 1 and 2 really dominate the whole data set, and cover type 4 is least represented. Since we are not really focusing on class imbalance and all that, we are more concerned about what each of these each of these parameters and hyperparameters, how they affect training. That's what we really want to look at in this data set. So what I did was I got rid of all these other classes, and you can see here there are 283,000 samples for type 2 and 211,100 samples for forest type 1, right?
Yes.
So in this cell, I mean, if you keep if you keep running the cells like further down, shift enter, keep going shift enter, or control enter, and you can come till here. You can come till here, and basically we have mm, knocked out class type 3 to 7. We made it a two class problem. Okay, don't worry about the code. So in the new data set, in the modified data set, there are only going to be two forest types. We're not going to worry about the class imbalance and all that. This is fairly balanced, so I think we will have enough representation. Okay. Have you reached this place, this point?
Yes.
Yes.
First, I'll just follow the screen. I'm still getting the error message, so I'm trying to go into a different browser now. But you can continue.
Okay.
Professor, I just wanted to share my error. It's a name error.
Yeah,
DF
please
is
share your
DF.
screen. Okay, DF is not defined. It means that you didn't run one of the previous cells, probably. Can you go up? Yeah, you see, after first cell, no. See, the markdown cells, they don't really matter to the flow of the class. The Python cells is what you should run. So after cell number 18, I think you didn't run the next two cells. Yeah, run that, and then the one after that.
Oh, okay. I'm sorry.
So I'm getting DF not defined.
Yeah, that's
All
probably
such
because,
yeah, so all
yeah,
such error can go away if you try to run all. That might
yeah.
take some time, but you can run it from the menu. There is a run all button just left side of the
Just,
text on the menu.
just right below the tools and help, you will find run all. Just click on run all, and it will run everything, top to bottom. Above,
Uh,
below tools and help, below tools and help. Above, go up, more up.
Section. There is a
Right,
file array.
right. Yeah, below that. No. Don't click on that. Don't click on that. Don't click on that. Don't click on that.
run
Just
all.
Yeah, just run all, yes, run all, yes.
Okay. Okay. Okay, that seems to be gone away.
Yeah,
Seems to have fixed it. Run all. Okay.
run all, yeah.
Oh,
So
there it
that,
is. Okay. I guess
okay, let's stop
I'm
sharing. Yeah.
good.
And that's for everyone actually. You can just run all. You can go cell by cell, or you can go to the top and just run all. After including the line that I have put in the chat box in the first cell, in the first code cell. Okay. So here we are trying to do a train test split, the standard thing that you would do in any ML problem. Please spend some time trying to understand what I'm trying to say here. This is I know this is a long description, but basically what we want to do here is, I hope you also know why we are using a validation set. We are not going to touch the test part of the data since we have so many data points. We have done a train test split, and within the train, we are keeping aside a smaller subset as validation set. That's what we'll be tracking to see if the model overfits or underfits or how it's performing basically. Um, so now we are going to start making the architecture, start making the neural network. Please go through all of these and try and understand. I think we have discussed everything that's there here in our theory sessions. These are parameters. These are the hyperparameters that we want. For now, keep batch normalization as false. We are not using any drop rate from dropout for now. The regularizer, you can just keep it to none, or you can use L2. People usually use L2 for neural network problems. Regularizer value can be, I mean, all these are actually default values. So people usually don't play with this much. The kernel initializer, you can have it as Glorot uniform. Again, we discussed what is the rationale behind this, but that's going to come to you as prescription now. So start with a simple stochastic gradient descent, and let's train our first model. Okay. Ignore all these. Now, here is where we would want to really focus. Um, okay. So one of the numbers that we are really going to be concerned about is this number, the number of parameters. So that directly um, comes from the number of layers and number of hidden layers and the number of neurons in each hidden layer. Okay. So can someone really tell me how I got this number 1760 from this 32? We discussed this briefly yesterday when we did our when we did the 28 by 28 image 784 and then three layers and all that. So this is just for this is a very similar thing but for structured data.
It is a fully connected layer, so 54 by 32, right, Professor?
Where did the 54 come from?
The input has a feature of 54 features, and the intermediate layer, like we have taken 32, right? Neurons per layer is 32 here. So the second layer, it goes to 32, whereas the first layer, 54 is the input, right?
Okay. So
In fact, like down the line, in the 17th one, you are giving a plot, right? Plus the model you are plotting. X might have got used, maybe capital X.
we got 1728.
Plus it takes one more. I don't know why. 54 multiplied by okay, then also it cannot be.
Let's
Yes, you're
let's do
correct.
it.
54 times 32. You need to plus the bias also.
Correct. Yes.
Yeah.
That's what I was to.
Bias is 32.
Yes. So the 32 bias terms, right?
54
So
bias term.
The
I
30,
mean, yeah,
the
32 bias
32,
terms for the 54 variables. Right, Professor? Is that
correct.
correct?
Yes. So the 32 neurons in my first hidden layer.
Mm.
So the 1760 comes from 54 times 32 plus 32.
Yeah.
yes.
Okay. So that's how we calculate the number of parameters at each hidden layer. Okay. And that's going to be very important because that's going to decide how much compute is going to be required to train this neural network basically.
Nathan, recheck when
Was
you get there. Can you let me know if Western Union is open? When you get there, could you let me know if Western Union is open?
what is it? Are you talking to me? Okay. Okay, so this is kind of the architecture that we have here. So the dense sigmoid input shape is this, and the output shape is 32. And then we have 1760 parameters. Okay, and this is basically what uh, um, sitting with a neural network would really look like. Okay, so I have 10 epochs. What is the batch size we are using here? The batch size is going to be 1024. And what is the size of my data set?
around 500,000 now, totally.
Mm.
And we have done a split with trying to split, so 80 percentage of it. So which means that 400,000 would be the training, right?
Let's go with that number. Yeah, probably.
And now this will be divided. So in 1024, that means like it will be done in 300, close to 300 batches, right?
Yeah, and that's what we see as the numbers. Yeah, the 310.
Okay. Okay. 310 by 310. Okay, fine. Got it.
Okay,
Hmm.
so we are sending in batches of data, not single line, single.
Hmm.
So the weight update is happening after every batch, right? And since our batch size is and since our batch size is 1024, we had a data set originally of four 80,000 probably.
Hmm.
And then we did a train test split. Within the train, we did a train validation split. So with the remaining data,
Hmm.
which I feel should have been some number like the number that I just have here, like 320,000.
It is
Uh,
it is coming to 494,000 or 495,000, Professor. Zero class zero is 283,300, and
yeah, that's before all the split and everything, no?
that's before split. So
Yeah,
495,000 and
mm,
test reservation is 0.2, right? So that means 80% of it.
80/20, yeah.
So it will be giving somewhere around 392,000.
Yeah,
And
within that, we are also doing a validation, test and validation
okay,
split.
got it.
Okay, so the number will add up definitely. And
Uh,
there will also be some approximation going on somewhere.
hmm.
So we can safely say that there are around 320,000 data points.
The phone is
320,000 data points, and that's what we see as iterations here. And the metrics that we would really look for is the accuracy. This is when I say accuracy, it is a training accuracy, the training loss, the validation accuracy, and the validation loss. Okay. Based on this, what can you comment on the training?
It keeps learning, training and validation and accuracy is following each other closely. So that means there is no overfitting or underfitting. I mean, training and validation is following close by. And similarly, loss is also approaching close by. And the learning has not yet reached its plateau. It is still in learning. Maybe a few more epochs could still give it its possibility to learn further. Now, currently, it has gone only up to 68% of accuracy, and
Yeah.
loss is also, but loss is reducing very slowly. Perhaps the maybe learning rate can be accelerated or whatever it is, or there can be additional neurons be added.
Yeah, so that's pretty much it, and that's what the next section talks about. So we don't look at the test data. We look at the validation data. We monitor any of the metrics that we want, and this is typically the curve that we would get. The Y scale is very misleading. It goes only from zero point 0.4 to zero point 0.6. Technically, it should go from 0 to 1. So one thing you can do is you can do something called plt.ylim. Uh, lim, I think. Yes, create the file and you can go something like 0. It should be a comma statement. Let me see if it works. Oh, I didn't run the whole thing. Wait, click on that. Okay. So what we basically saw there was that the model is still learning, right? So the first thing that we would want to do is increase the number of epochs, right? Because we didn't reach a satisfactory level of training. Okay, so the first modification that you will do is go find the epochs in this. I didn't give that as a param. Epochs is here, right? So epochs is 10, probably change it to 20, and don't run from top, run from here, run from this cell, everything down. So you can go control enter till the end. That is the first change that I would want to make in this session today. Increase the number of epochs to 20 and rerun everything downstream.
Yeah, now it reaches the plateau.
Can you share your screen?
Sure.
Yeah, it has reached almost 75% accuracy.
And it stopped with that.
No, it continues to go up. I think it can go a little bit further also.
Okay, now what is your inference from this now? Is there anything else you want to change?
I think we
You
can
want
try
to,
maybe 25 epochs.
okay, increasing the number of epochs is one thing.
Mhm.
But what is the clue that you're getting from the neural network that, with this, the network is learning, but what's happening? It's learning slow, right? The learning is slow. So what we can change?
We can increase the learning rate.
Exactly, right? So instead of increasing the epoch, now we know that the trend is good in the sense the network is actually learning with the given data. But what's happening is the learning is a little bit slow.
Mm.
So one way to address that is increasing the epochs. But even then, how much epochs are you going to increase? Like 25, 50, 75, right?
Yes.
So you can fix the epochs to maybe 50 or 70 or something, and you can try to change the learning rate.
Mm.
But Professor, one question here.
Yeah.
It seems to be plateauing here, right? The accuracy.
I didn't see that. Can you show your
I'm
screen?
I think it increases. I can share my screen to show that. I think it
Yeah, sure.
increases in this. Yeah.
Yeah, sure.
Is my screen not visible? Okay.
No, your screen is not visible.
Okay, I am sharing. Just a minute. Okay. You're able to see now, Professor?
Yeah.
Yeah. Okay. So what I'm asking is,
Yeah. Now this is definitely, well, yeah, it's not completely flat. I wouldn't say that the training is complete.
mm,
So when the training is really complete, you will see like a really flat line,
okay.
like something that's parallel to the x-axis, almost parallel to the x-axis.
Okay. So it has some more,
Scope to learn. Yeah.
life to go.
Yes.
Okay.
Yes. Yes. Yes.
So
So
Gentlemen, I'm
everything
not even
about
close to that.
okay, share your screen. Do you have any issues or your training is just slow?
I don't know. It doesn't look like it's slow. It's just not. It's. I'm certainly not getting anywhere like a plateau. Let me just share my screen, okay?
Sure, yeah. Mm,
So I'm wondering what did I not change?
okay. Okay, go a little bit up. Show me show me stop there, stop, right. No, the training. Show me the training. The values, yeah, this yes. Epoch 1 of 10, yeah, this. Okay, so it's still running only 10 epochs, right? So go
Oh,
up.
maybe I didn't run.
Oh, you have to run everything. So go up.
Maybe just hit that run all.
Uh, we don't have to just, that's what I'm telling. So go up a little bit. Go to the place where you change the parameters, the hyperparameters. Yeah, here. You change the, yeah. So everything downstream we run. You don't have to run anything above this. Anything below, everything below this run once. Yeah.
So, Professor,
Yeah.
means if the model is still learning,
Mhm.
means it is not yet overfitting.
Yeah. It is, if we stop early, then that would be underfitting. Yeah.
Okay.
If we stop before the learning is complete, that would be underfitting.
Okay.
Hmm.
I increased the learning rate and kept the epochs to 40. I got a flattening plateau phase on accuracy and loss.
Okay, show me your screen. Let's see if that is really the matter
Yes,
that I'm looking
I
for.
am sharing my screen.
Yeah.
Just a minute. Okay, you are able to see this, Professor?
Yeah.
Okay.
Yes. So this is exactly what a plateaued learning would look like,
Mm.
right?
And,
So that's
now,
around 78%.
yes, exactly. So it comes to, yeah, 77.8. Yeah.
Yeah. So around 78% accuracy is what we are getting there. So now we know that the model cannot perform any better than this,
With
right?
with these many neurons, right?
Yes, with this setup, yes. So
Mm.
don't run the test yet. The test we will look at it only once
Yeah.
after we are happy with our
Okay, okay, okay.
after we are happy with our model. That's when
Mm.
we will test it on the test data, and that will be it. That's all.
Mhm, mhm.
Okay. Okay. So all right. So what is it? What do you want to change now?
The hidden
Yeah.
layer shall we increase?
Okay.
The,
You want to go
or the number
go.
of layers we can increase, right? Professor?
Yeah, you can do that as well. Yes.
So if if I'm increasing the number of layer, basically tapering the layers also would be required, right? I need to give it like 64, 32, 16, something of that sort.
Uh, yeah, or 32, 16, 16, or 32, 16, 8. 1
30,
minute. Just
yeah,
one.
yeah.
Before we go there, let's see if everybody has got it. So before we change the parameters, why don't we change some of the hyperparameters?
Mm-hmm.
Um, or think about changing the hyperparameters. Now, what we have implemented here is stochastic, like a normal stochastic gradient, SGD.
Mm-hmm.
And then we have other options, ADAM and RMS prop. But remember, the advantage of this, at least in theory, comes out only when we have deep neural networks. Right now, we do not have a deep neural network, right? Only two layers. So, is there anything else that we can change here?
We can reduce the batch size, Professor, because maybe it is averaging out some learning.
You can try that. There is absolutely no reason for it to be 1024. People are just sometimes obsessed with the 2 power something number. So that's the only reason people have 1024, 512, 256, all this. So you can just give your lucky number. So if you want to go 512, that's completely fine. Or if you want to go 500, that's fine as well.
Yeah, trying that.
Okay, you can try that. The point of the session is to explore these things, so you can actually try that. Let's see how it works out, and then we can change the whole architecture if required.
Even Adam stands for adaptive momentum, right, Professor?
Yeah,
Even that works only with the deeper
it's
layer.
not like it works. It will work for anything actually. It's not that it will work only in such situation. The true power of it, I think, would come if you have deeper network with a lot of dimensions. Remember, the problem was
Hmm.
the multi-dimensional space. If we go deeper, we
Hmm.
are just having more and more like 64 dimension space, 32 dimension space, and all that.
Hmm.
Right. So the more the complication, it's harder to find the global minimum.
Hmm.
So it will still work if you do add-on here. There's no rule of stopping you from using it.
Got it. Got it. And by changing it to 512, 1% increase in the accuracy, and last comes to 46.95, but it touches the 78 and the accuracy.
Okay. Okay. So how about the others? Shall we just go ahead and change the architecture now? We'll just make it deeper. Who
Professor,
wants to
can
who wants
uh,
to go deeper? Who wants to add more neurons in the two layers? Who wants to go something like 128 and 64? Who wants to go 3, 4 layers and start and then do 64, 32, 16, 8?
I want to go for more layers.
Okay, Niaz wants to go for more layers. Who wants more neurons in the two layers?
I can go with more neurons.
Okay. So at this point, it sounds like we're just going fishing, right?
Yeah.
Did we not test them individually and look at the results individually?
Like as in individual results, as in what is it? Jeff?
Changing changing multiple parameters and
Uh,
then looking at the results doesn't tell us what the impact of each change
right.
is.
So
Or
yeah, that's what we were discussing. Now, what are the things that we can actually change here? We can change the number of layers, right? We can start with this. Really, this changing this doesn't really make sense because this the effect, not only this, the effect of everything else here, like changing SGD to Adam or increasing the learning rate or everything else makes sense only if we go deeper, right? Because all these are problems, all these are solutions to deep neural network problems. Remember the vanishing gradient and the optimizer issue, everything that we discussed in the DNN session, right? So that's why we are not changing anything. The only thing that we can actually control now is the batch size. We're trying to see if increasing the like reducing the batch size would make the learning better. Because the assumption here is we are setting 1024 rows of data at a at a stretch to the neural network to learn from. So the thought process was maybe if we send a smaller batch, it will learn better, but that didn't make any difference. So everything we have increased the number of epochs. I think we have a case with 40 epochs where where the network doesn't learn more than 77, 78%. So the next logical thing is to so now we have arrived at the conclusion that whatever we do, the network is not learning the patterns, learning the features in the data, right? So that's why we are now leaning towards changing the hidden layer and the neurons in hidden layer. Now I gave the class two options. I asked the class, how many of you want to go deeper? So by deeper, I mean have four hidden layers and go something like 64, 32, and probably 8. Okay, this is one option. The other option is to go to only two hidden layers, but add more neurons, like have like 128 neurons and 64 neurons. Some of you are opted for this, some of you opted for going deeper. So that's what we are explaining now, exploring now.
Okay.
That's the logic
Thank you.
actually.
Okay. Thank you.
I may have jumped the gun, but I've changed from sigmoid to ReLU and I've got 81 and still not plateau yet.
Okay, that's fine. If we go deeper, we might want to actually change the problems of the DNN. Okay. Uh, so the next case that we can do here is I want to personally do this. I want to do add more layers, add more neurons to the two existing layers. Okay. And I want to keep everything else the same. Let's see how that works out. The smaller batch size.
Yeah, ReLU is miracles. It goes up to 84.
Okay. So obviously, so here I just increase the number of neurons in the two hidden layers.
How much you have chosen, Professor, now?
I have 128 and 64.
Okay. I have chosen 3 layers with 64, 32, 16 with
Okay.
ReLU, and I could get 684%. And what I was seeing is with the sigmoid, it does a kind of a delayed takeoff. It has the initial plateau and then later it thinks and learns. Whereas with ReLU, it does a immediate shoot up.
Okay. So if you see here, it's stuck at 77.5. So here at this point, I'm not going to waste my compute and I'm just going to stop my training. Okay. So I saw that the network is not learning beyond 77. So I have 77.46 and then 52555762664. I mean, it is slow, but it is kind of plateaued at this point, at least the validation. If you look at the validation data for from epochs 11 to 19, it has changed only from 77.1 to 77.5. And for around 3, 4 iterations, it has remained close to 77.5. Okay, so that is an indication to me that the network is probably not learning. And if I keep doing this, it might actually overfit. And if you see this, this has gone to 78%, whereas this has remained at 77.5, right? So I'm finding clues for overfitting. So I stopped the training manually here. Now there is a hidden way to do this actually. There is an inherent way to do this. Something called, you can include something called early stopping here. And you can ask the network to just stop training if the network doesn't learn beyond a particular value. Okay. Uh, what I did manually, now you can automate it basically, right? So what I'm inferring here is the network is not learning even though I've increased the number of neurons in the hidden layer. So I'm going to go deeper and I'm going to have 3 layers and start with 124, 38, and 32. Okay, so the first layer is going to have 128 neurons, second layer 64 neurons, third layer with 32 neurons. And once I go deeper, what's going to happen is all the vanishing gradient problem is going to come up. So I'm going to change my sigmoid to ReLU. Okay. And dealing with big numbers is going to be difficult. So I'm going to use a batch normalization. I'm going to have batch normalization true. And again, since this is a deep network, I'm going to use a regularizer. I'm going to do L2 or regularizer. So why am I changing so many things suddenly? Because the only reason is I went deeper and I am foreseeing problems of deep neural network to manifest, like vanishing gradient, difficult to optimize, difficult to regularize, difficult to initialize, all these I'm expecting. Okay. So, all right. So I'm foreseeing those problems and I'm changing these things accordingly. Hidden activation, change to ReLU, using batch normalization because the numbers might be too difficult to handle, using L2 regularizer, and SGD, stochastic gradient descent, most likely might not work. Um, yeah, most likely might not work, but since this is a demo and if I'm training this by myself, I would immediately change the SGD to Adam or RMS probably Adam. Okay, why? Because from experience, I'm going to kind of say that most likely SGD might not work. Okay. But since this is a demo and we are here to learn, I'm going to leave the hyperparameters unchanged. I'm going to have only the parameters here. And let's see how this turns out.
Or I get a name error again.
Okay, can you share your screen, please?
If I entered something in L2 regular.
It should be in quotes section. You can put a single quote in the left and right of L2.
Oh,
Yeah, double quote, yeah.
Either one works similar.
Yeah, either it just has to be a string.
so I can copy change line.
I didn't get your question. What is it? You want to?
Copy the just copy this line here, the green line. Or
Yeah, yeah. Yeah, just do that. Yeah, I think it's suggesting you to do that.
yeah,
You can take the suggestion or just manually add the two
yeah.
add
Okay,
the double quotes before and after L2. Or just copy what I have. Let me share my screen real quick.
okay.
So just copy this guy here. That's all. Anything after the hash, it's not going to consider. The code is not going to consider. So that's just for us to like comment and see what are the possible values which can go here. So just copy this and delete it and paste it here. That's all. Should I increase the font size of my collab?
It's good enough, also.
Okay.
Professor, can I
Yeah.
ask some question very preliminary? Is
Sure. Go
that,
ahead. Yeah.
yeah, how to distinguish accuracy and the validation accuracy? How to interpret the two fields?
Okay. So you remember how we split the data into training and validation, right?
Yes, yes.
So the training accuracy is the accuracy that we get from the training data. The validation accuracy is the unseen data that is being tested on. Like we are setting aside 20% of the data as quote unquote unseen. That is going to act like new data points and it is going to make a prediction using the values, using the weights that it learned from the training data.
So I got, yeah, based on the current recommendation of parameter, I just got a nearly 86% of accuracy with training and validation accuracy very close to each other. So is
Okay,
that means it is very consistent and does not occur overfitting or something?
very likely, yeah.
Yeah, I'm just to double sure. Can I share the screen to you
Definitely,
to
definitely,
validate? Yeah,
yes.
yeah,
Yeah.
yeah.
So ideally, your training accuracy and your validation accuracy should be very close to one another.
So this is my uh, result.
Okay. So what we observe here is the network is still learning. The network has not flattened out yet completely. Like we don't see in a completely learned network or a plateaued network after convergence, the orange and the blue line will almost be parallel to the x-axis. Okay, so what we observe here is it is still learning, it is still going up. So I think this is where we can actually increase the number of epochs and the network might actually benefit from that.
Oh, okay. Thank you very much.
Yeah, and that's what my network looks like as well. Okay. See, the loss is still falling. It's not completely plateaued yet. I'll probably change just 0.5. Yeah. Okay, so what I'm observing here is there is a 90.3, 90.7, 90.34. Okay, 91, 90.9. Okay, so this could go either way. So I would slightly uh, be concerned here. I have a feeling that this is more because of the stochastic gradient descent that we are using.
Professor,
Okay,
can you show the plot, like how smooth it is?
it's not very smooth. Actually, the validation curve is not very
Recalculate it
smooth.
is okay. You run everything down. Okay.
Okay. So what I'm going to do now is I'm going to change some of the I change some of the parameters here, right? Uh, the clue to not change this anymore is that my accuracy is reaching somewhere around 90% with this, okay? Which I'm quite happy about. So I'm not going to change the number of hidden layers or anything. I'm trying to see if I can tweak it. Okay. That's when I would start playing with my hyperparameters rather than my parameters. Right. So the first thing I would do is I would probably change the momentum to some. I would include a momentum characteristic, momentum aspect here. So the gradient descent is going to remember some of the previous values before it's going to make an update. So it's going to forget some of the old values and it's going to remember only the past one or two values for making an update. So I'm going to run this and see if I can still work with stochastic gradient descent. And meanwhile, if I look at the number of parameters here, I'm getting new numbers. See, previously I didn't have something called non-trainable parameters. Now I have something called non-trainable parameters. Uh, Let me explain the new architecture here. Dense 13 is 128, 70, 40. The 70, 40 is probably 128 times 54 plus 128. Okay, that's where the 70, 40 comes from. Um, but we are also adding a batch normalization where there are 512 parameters, which is introduced by batch normalization. You see, when a batch normalization is the process, the nodes are here. Okay. Um, the batch normalization is not affected by the gradient descent. So it is not strictly a trainable parameter, but it is something that the network remembers. Stuff like the moving mean, moving variance, and all that. These are values which are introduced, um, which are introduced because of the normalization that we are introducing. Okay. So what it basically means is it tries to shift all the data points around zero, right? So if you remember the plot that I showed in the class, we are trying to move all the columns centered around zero with some sort of a common mean and some sort of a common scale. Okay, so it is actually calculating these means and scales and is doing the shifting in the back end, and it has to remember some of the values, and that's what the non-trainable parameters. So these are values that the network remembers for the sake of batch normalization, but the it is not the part of the training as such. right? So that's why they are non-trainable parameters. So the total parameters are 18305, which is like the addition of all this. Out of this, the parameters that come directly from the neural network, from the hidden layers, and the neurons in the hidden layers is 17,857, and the non-trainable parameters are 448. This came into the picture because we changed the use batch norm to true. Okay. Now let us go back to our network and see what's happening there. Okay. Some good news.
What is the change now?
What is it? What?
What is the change recently done?
Okay. So I gave a momentum value. SGD. Still we are using the 3 neural network.
Okay.
Still SGD, but there is a momentum 0.9.
In the SGD itself. Okay.
Yeah. So stochastic gradient descent with momentum. Okay, so the accuracy has increased 92.1. I think from epoch 34 to 40, it has been stable. 92.11 to 92.16 is the training. And the validation is also pretty stable. It is saturated at 92.03. So the network is not going to do any better after this. So this is what a plateaued network would really look like. How you see this is almost parallel to the x-axis, right? It need not go to these many epochs. I could have stopped somewhere over here, okay? But I just let it finish the process. And this is what the nice loss would look like. Is it capable of improving? Definitely yes. Okay. So let's go ahead and change the SGD to something like Adam or RMS prop. I'm going to straight away go to Adam and
You have to change the beta 1, beta 2, right? Otherwise it will give error.
oh yeah, correct. Yes, correct. Yes. Okay. So go ahead and change the Adam 1 to 0.9 and Adam beta 2 to also 0.9 or 0.99 values. Where is it? Okay. What to do?
I applied
Sorry,
0.9.
Professor. Can
0.9.
you explain what is beta 1 and beta 2 again?
Okay. So we did it in the theory session. Okay. So one of the ways that you can actually control the weights is you can give a momentum value. The momentum is the stochastic gradient descent, how much it is going to remember some of the older values, right? Usually a starting point for that is zero point 0.5, but usually the prescription is 0.9. People just stick to 0.9 or 0.95, somewhere around that value. So basically, lower the number, uh, lesser is the acceleration, which means that it is going to remember some of the uh, lesser older values. Okay, so zero is pure stochastic gradient descent. There is no, there's nothing that it remembers from the previous updates. 0.1 is it remembers like 10%, 20%. So it goes like that. So 90 is now 0.9 is it remembers a lot of its previous values. Okay. So that is the momentum that we have here, and that is actually the beta one that we have for Adam. The beta 2 for Adam is basically how much we are going to penalize. So now the problem here in the neural network is if we adjust one weight, then correspondingly the other weights might not might be affected more or less. Like for example, for the same zero point 0.1 value, 0.001 value update, um, if the weight is already zero point 0.9, it will have X amount of effect. But if the existing weight is 100, 100 plus 0.01 will not make much of a difference, right? So the beta 2 basically corrects for that, corrects for the different existing values in the weight, and it penalizes big updates and it rewards slow updates. Okay, so that is beta 1 and so that is the idea behind RMS prop actually. Adam just combines the SGD with momentum and RMS prop. So the beta 1 is the same momentum that we have for SGD. The beta 2 is basically the hyperparameter that we would have for RMS prop. How much of penalization we want.
Thank
Okay,
you.
so those are the numbers there. So with these numbers, let us do the training again. You guys can do it too.
So we have a
Professor Adam, one is must be always the same with the above one or
The momentum,
yeah, the momentum.
it need not be actually,
Actually,
but that's what it usually means. So the you see these are two different optimizers, right? So they don't talk to each other. So Adam and SGD they don't talk to each other. But I'm just explaining where the zero point 0.9 comes from. That's all. So the zero point 0.9 here basically is the zero point 0.9 momentum of my SGD. That's all. So it's not like these two optimizers are talking to each other. No, that's not happening.
yeah, thank you.
I see that SGD with momentum, it able to go up to 93% accuracy with a loss of 0.23.
Yeah, I got 92 with that.
Now, whereas if we are using adaptive momentum, it gets stuck at 84.5.
Okay, then we might want to implement a decay.
It's I have seen in the code LRDK. Okay, momentum decay you are saying, but
Learning
Adam
rate decay.
LRDK was there somewhere.
I think
Okay,
it's set to false.
okay, if set to false. Okay. We have so many controls, right?
That's why we are going step by step.
Hmm.
But if you look at it, if I change the number of hidden layers, automatically A lot of the other controls, they automatically change. We set them to some default values actually. Yeah, I think even my network is stuck at 85 for with Adam.
Yes.
Professor, if I
Professor,
can share my screen quickly.
Professor, does it mean that the SGD is better than Adam all the time, or just in our case here?
Yeah, I think in this case it just turns out like that. And it is actually quite common that you will find SGD with momentum sometimes working better than any of these complicated atoms and the RMS prop. You can actually try RMS prop alone instead of atom. Okay, what is the question here in the screen?
Yeah, hi, Professor. So I don't know why this is like, so it's not very linear model.
Correct. It won't.
So,
So this is very likely atom, right?
yeah, this is Adam, yes.
Yeah. So this is a very common thing with Adam.
Okay.
It happens because the weight update is as you said, it's not very smooth.
Okay. Okay, got it. Thank you.
Hi, Professor, can you hear me?
Yeah.
Yeah, maybe I didn't hear you right, but why is the training versus validation accuracy graph is not very smooth? Why is that?
Because we move to the Atom optimizer, and the way the weight updates happens in that is usually not very smooth. I think I also showed this in one of the sessions. Is deeper better? I think session 4 should have answer to this.
Got it. I'll look at that. Thank you.
Yeah.
Yeah, Professor, just share my little feeling along the training. Just guessing each one is trying to find the path in the dark. That's my feeling.
Each optimizer, you mean?
Yeah.
Yeah, correct. Yes.
Yeah, we are trying to make the best configuration for the optimizer to walk
Correct.
with this best path to the goal. And
Exactly.
ultimate goal is to find the universal minimum.
The global minimum, yes.
Yeah, global minimum. Yeah. Thank you.
So what did I get? Yeah, so even my network is stuck at 85. I mean, from epoch 30 around, it is stuck at 85. The last 10 epochs are completely pointless. Okay. So one last thing we can try to do is we can try to change the learning rate decay. So I'll share my screen again. That's the only thing I think we did not really touch. So learning rate decay, if I set it to true instead of false, that just dynamically changes the learning rate. So after how many steps we want to change the learning rate, I'll just keep it at 1000. Um, by how much? I think I'll have something like a 0.9 or something, which is basically saying, um, after every 1,000 steps, make like a small change in the learning rate. Okay. So you can have it at 0.9 or 0.95 also. I'm going to leave it at 0.9. And this is the last thing I'm trying. The reason I'm doing this is I'm a little bit concerned that the network is probably stuck in some local minima and it is not able to get out of it. So I'm trying the decay value.
So, Professor, why the result, the accuracy is different from you, even I stick exactly what you configured.
Ah, so that's because your weight initializations are different, right? The starting weights for your neural network is different.
Is it random?
But
Or
it's of course it starts with a random number, but really it won't be the difference between day and night. It will be like very small difference, but not hopefully not a very huge difference.
yeah, that matched up my observation. Thank you. So the difference is very small now.
You see how with the updated configuration with the learning rate decay implemented, it was initially stuck at 85%. Now it is reliably going towards 89% accuracy. Right. So really part of the problem was because it probably got stuck in some sort of a local minima and it was not able to go from there. And by implementing DK, we actually addressed that issue and we have moved past that. And it is still not overfitting. You see how it's 89 and both the training and the validation are comparable.
And how much is your initial learning rate, Professor?
0.1, I think, 0.01 or something.
I kept 0.2 for trying out and I got stuck at 86. Okay.
Okay, now I think we can take a break and come back after the break and we'll continue. I think it's stuck at 90% now. It's not going to go beyond 90 probably. Yeah, it's probably 90. Okay, so let's take a break and let's meet up.
So what time are we resuming?
Yeah, sorry, I just unmuting to say that. Since this is pretty late, let's do a short break, like 5 to 6 minutes, 6 or 7, 7 minutes, I think. 7 minutes is good. Thanks. or return back.
Actually, the learning rate is the issue for Adam. If we
Yeah.
go to 0.0005, I mean, half of zero point zero 0.01, it
Mm.
reaches up to 92.5 also.
Yeah, probably. Okay. So I hope you got the idea here, right?
Hmm.
With the first notebook, what we tried to do was so now there is some meaning to the madness, is what I hope if you are able to appreciate that, I would consider the notebook a success. So it's not that we are just madly adjusting a few screws and then seeing, okay, let's see what works best. We are doing it in a very informed and um, in a slightly more systematic way, right? I hope you are able to appreciate that. How but what we started with initially with two layers and all that, that is a little bit, you will learn that by experience. But tuning the parameters and tuning the hyperparameters after a particular point, depending on how the network actually trains, the legacy term for this is babysitting the network. So you look at the network and see how it trains, how it progresses. And depending on that, you will kind of, if you know enough about the neural network theory, you will know which knobs to adjust for you to actually get the correct result, right? So I think with a good combination of Adam and the learning rate and beta 1, beta 2, we can reach some reasonable level of accuracy. I think 93, 94 is what we can actually reach. But I think if we are able to do 92 is also anything more than 90, I think I would consider that success. Okay. I hope everybody was able to reach that level of accuracy for this particular data set. Okay. So I'm going to share the next material to you. You give me 1 or 2 minutes and renaming some. Okay, so in the prism with the let me see if we have it upload today. Okay, so you will find mnist underscore ann underscore cnn underscore autoencoder.ipynb in the in today's material. Please go ahead and download it and let's open that in the Colab.
So where did you paste the file? Oh.
In today's material. Are you able to open it?
Yes.
Upload it in Collab and open it, please.
Yes, we are able to open.
Professor, I think we should just go ahead and run all right for this one.
Yeah, yeah.
Yeah,
See if all the cells when.
yeah. Okay.
Let's just test that first. Make sure there are no errors.
Sorry, you give us another lab from where? I think I missed that.
What's that?
We're running a different lab, right?
Yeah, the second notebook. So I've uploaded it under today's resources. So this is basically the MNIST data set. So did it run without error?
It's still running, Professor.
Okay.
But, yeah.
Professor, I'm getting a field popping up. Type to choose a kernel source. I'm in VS Code.
Okay, you can share your screen. You can just type Python in that and think it will. Oh, am I sharing my screen? Sorry, but I was not. You can share your screen.
Yes. Trying to find it. Okay, here we go.
Okay. So, okay.
When I go like this, there's the field that says type to choose a kernel
Yeah, okay.
source.
Just type Python in that. Oh, he's giving you options. Okay, delete that. Let's see what options it's giving you.
Install
Yes.
enable suggestions.
Okay, so you don't have the Jupyter Notebooks extension. So how did you run the previous notebook then? Did it run?
Yeah, it ran. It ran
Yeah, then enable
easily. I
it.
don't
Yeah.
know.
Yeah, just enable that extension. Yeah.
Okay.
That should work now.
Install running cells with Python requires the IPY kernel package install.
Yeah, it does. It does require that. Yes. I don't know how it ran without this package previously. No. I mean, that's a required package to run this in VS Code.
Module not found error.
Okay, so you have to install the module actually. So you should probably do a pip install. So what I would suggest is upload the notebook into ChatGPT and ask for a pip install line. So ask what are the dependencies that I should run. And it will give you something like pip install and a list of things that you need to install. And see, that is the advantage with running it in Colab. So all that
Okay.
is pre-installed in Colab environment. So environment.
Is
So
there a way? I mean, I can go to my Finder, and I'm just wondering if I should just try instead of doing all of that, just running it in Colab.
yeah, you can just run it in Colab. Yeah. So just collab.google.com and upload this file there and just run all. That's all.
Okay, what is the address again?
It's there in the chat box. Welcome to Colab.
Okay, yeah.
Okay, so let me share my screen real quick. Okay, so the data set is the infamous MNIST data set. So these are numeric. So these are numbers, digits, and the task is to um, identify the digits actually. I think you should mute yourself if you're not talking to me. Okay. So all these are dependencies, not knowing much about it. So we are getting the data from a public, from some repository using an API call, signal that. So this is what the data set is going to look like. So this is randomly picked some sample images and it's 10 by 10, so it should be 100 images. You see how you can really understand the complexity of the task. So this is one, this is one, one. So all these numbers are one, and there's a six, and this is six, and six is probably the hardest because people do all sorts of thing with six. This is number two, and three and eight are probably also a little bit difficult to identify. People you get you some error with three and eight as well. Zero and six. So you can see how complicated the data set is, right? So as always, we start with a training repository. So there is actually somebody sitting and classifying this image as zero, this as one, this as two, this as three, this as four, right? And that repository exists, okay, before even we start training. And that is the correct answer based on which the network is going to train. We are doing some pre-processing here. We are converting the 0 to 245 to 0 to 1 values because it's just easy to deal with the smaller numbers. Okay, so that's basically the only pre-processing that we are doing. And as I said yesterday, where we are going to flatten the image and we are going to send it not as like for ANN. Okay, before we go there, let me backtrack a little bit. The goal of this network is to train two types of networks, ANNs and CNNs, and see the performance in both of these, using both of these for the same data set. And as we discussed yesterday, the ANN approach is slightly different. The CNN approach is slightly different. This is going to be a fair replica of what we just did in the other notebook. But here, this was structured data But here it was, this is image data. That's the only difference. Everything else is going to be the same. As you can see, what is the shape of this neural network? Can anybody tell that? Can anybody see? What is the architecture of this neural network?
Shallow, right?
It's a shallow network, just one hidden layer.
Yeah.
One input layer, one hidden layer, one output layer. That's it. Okay. And we are slowly increasing the complexity. We're training for 4 epochs. And the second model has, oh no, I think there are no hidden layers here. Yeah, there are no hidden layers actually. So there is one input layer and one output layer. That's all. So this 10, this is actually the output layer. Okay, so it directly maps the 784 input pixels to the 10 output classes. And then we are creating the second neural network with one hidden layer with 100 neurons. Okay, the activation is ReLU. Probably a sigmoid will work here. You can change those parameters and you can play around with that. I would not really change anything else like the Atom or RMS prop or anything. Uh, okay, so this is the second network. And then the third network, again, I'm trying to create parallels between the last week's lab and this lab, like the lab that we just completed with the forest data and this. So just comparing the different optimizers, the stochastic gradient descent, RMS prop, Adam, and all that. And these are the plots for that. Okay. The next thing I'm doing here is I'm deliberately doing some overfitting, right? So as you can see here, I got a reasonable level of accuracy, like 96, 97% accuracy, even with one hidden layer of 100 neurons, right? So I am deliberately making an overkill here with 3 hidden layers, 1024, 2024, and 512 neurons, right? The reason being, I want to show what is overfitting and how overfitting manifests in image data. So, and I'm doing it for 25 epochs. As you can see, I'm reaching a reasonable level of accuracy even by the 11th epoch, right? So by the second epoch, the network has probably is done with its training, 91 and 90. Okay. This is slightly okay, but anything after the fourth epoch is definitely overfitting. As you can see here, I'm getting a 95, 98% accuracy in my training data, but in my validation data, I'm getting only an 89% accuracy, 11 to yeah, around 10 percent difference, which is not very acceptable, right? And by the 25th epoch, I'm reaching 100% accuracy. So it is completely ungeneralizable at this point. It has memorized the data, and the validation accuracy has stopped at 92, 94%. Even that is probably an overkill. Okay, and you can see that it has reached 100% here. Now, what can I do to reduce the overfitting? Um, of course, I can reduce the number of layers, right? But if you look carefully, I'm actually getting an accuracy of 98, 97. My validation accuracy is also something like 94, 92, right? So I don't want to compromise the network's depth and its ability to learn. So I want to preserve the architecture in some form, okay? But I do not want overfitting to happen also. That's when I would go for a deeper architecture, 512 neurons, 256 neurons. Okay, it's still densely connected. but I'm including a dropout layer here. 0.3 is 30% dropout. Okay, if you remember the concept of dropout, it is basically um, in few forward pass, in few iterations, a few neurons within a hidden layer are kind of turned off. So they don't really learn the data. So the output of the previous layer actually goes to the next layer directly. Okay, so that helps. So that helps in the network not memorizing the data. Okay, so as you can see here, the dropout works. Okay, but I would not go as far as to say that it is perfect here. Of course, it's a demo class. Realistically, what I would do is I would probably stop with the sixth epoch or somewhere that point. I would stop the training. Okay, so I'm getting an accuracy of 99% and a validation accuracy of around 92%. There's a 7% difference. I don't know. I might not be very happy with this. I might change, I might do a few other runs, but I will definitely save this model and I will keep this model aside. But I will definitely try to make some tweaks and see if I can close the gap between the training and the validation accuracy. Okay, so that is dropout to mitigate overfitting. Now, finally, I'm implementing CNN, which is what we basically discussed yesterday. Now, the only difference is instead of layers.dense, I have layers.2D, layers.con2D. So con2D is basically the two-dimensional convolution. The first number is 32. So that's 32 filters or kernels. Each kernel is of size 3 by 3. And I'm using a activation function ReLU. Okay. After that, the next layer is a max pooling layer. The max pooling is 2 by 2. Here again, I can have hyperparameters like stride and all that, which I have not included here. Okay, but definitely I can include that if required. That can be part of the mix here. So there is a second hidden layer, con2D, with 64 neurons, again size 3 by 3, ReLU. Okay. Usually the first layer has more neurons than the second one, but in convolution in CNN, this is also possible. The idea being there are lesser low-level features and more high-level features in the data set. That's possible. You can do that. There's nothing wrong in that. And then there is a max pool layer here. So till here we have extracted the features. Now these features, they go into my ANN for classification. So layers.flatten, whatever output I'm getting from my max pulling 2D, I am flattening the 2D image into a big array, okay? And I am implementing the classifier. The classifier basically has 128 neurons. The activation is ReLU. Again, I'm implementing a dropout here because I don't know, I just want to be careful here. I want to reduce overfitting. This is my prediction using softmax. This is my whole architecture. Remember, I have not included batch normalization, any of that. It's very much possible. Whatever hyperparameters we had here, whatever parameters and hyperparameters we had here, very much possible to implement everything in my CNN as well, right? So that would just be one more layer here, layer dot batch norm or something. Batch norm, just it's just need to stack it up somewhere. And then I'm training my network and I'm getting a training accuracy of 98% and a validation accuracy of 99%. So I'm fairly happy with this because the training and the accuracy are both at 99%. So although the accuracy is high, suspiciously high, they follow closely with one another. So I think I'll be happy with the performance of this particular network. Okay. And here is where I'm inspecting the prediction. So I'm building the model here and I'm using the model to make a prediction. So I'm randomly picking images from my data set and I'm sending it into the model and making a prediction. And the prediction is 7. The true number, correct value is, the correct answer is 7. So true and 2, 1 and 1. Does a fairly good job. I think this is the only place where it fails. It predicts it as 0, but the correct answer is 6. I mean, we can see kind of where it really comes from, right? Mm, okay, so that's how we are comparing the ANN, the ANNs and the CNNs. Finally, we also did a small session. We did a like a session on autoencoders, right? And here I'm including that also as part of this lab, where I'm reconstructing an image by using the autoencoder concept. So basically, I have my input layer of 784 neurons. My first encoded layer has 32, and that basically serves as my bottleneck layer also. Okay, you will see how surprisingly effective this actually is. This very simple architecture. So I have 784 input, 32 as my bottleneck, and 784 as my output, right? This is a very simple autoencoder, very elegant architecture with 32 neurons as the bottleneck. But even that is surprisingly very effective. As you can see here, this is my original and this is the reconstructed image. Two original, reconstructed, original, reconstructed. You can see how the reconstructed image is very close to my original image. Okay, so that's basically what we are trying to show here. You can run the notebook and see if there are any errors. See if you can follow what's going on in the notebook. I think it's fairly well annotated. Um, try to play around with the hidden layer here. Uh, how you would add more hidden layers is basically copy this and kind of paste it. And that's it. You have one more hidden layer and one more match pool layers. This is your new architecture, basically. See? Okay. So yeah, so try to change the dropout. Where is the dropout? Dropout. Yeah. Try to change the dropout to 0.2. Okay, you can try to include a dropout here. Usually people don't include a dropout here because we don't want to mess with the performance of the convolution, but sometimes that happens as well. Dropout is usually implemented in the fully connected layer in the classifier part of the CNN. You can also change some of the parameters here. Dropout can change it to 0.2. You can change the architecture, change it to 256 and 128 and see how the network performs. Okay. So please go ahead and run the notebook and see if you are able to catch anything intelligent. How many of you are able to run the notebook without errors?
I could complete. Yes.
Okay. Were you others were you able to change anything, or even yes, anybody were you able to change anything and see how that reflects?
No.
I'm still trying to run the first set of notebook, Professor. I've not
Okay,
completed all the steps. Yeah, yeah. I
the
think because it
first.
has an image, so it is taking a little bit longer.
Okay.
Yeah.
Did modify now, Professor? Perhaps later we will offline we will do and experiment with it.
Okay. Let me quickly do something else, show something else as well. Again for your offline work. So this is again the same thing that I have done using MNest, but this is a different data set called CIFAR 10 data set. This is color image, RGB image. There are 10 categories of items here: airplane, automobile, bird, cat, deer. You can read this. These are the 10 categories that are 10 categories of images in this data set. And the flow is going to be very, very similar. That was 28 by 28, but these are 32 by 32 RGB image. So it's going to be a lot more parameters, right? So if the ANN fades here, you will be able to actually see, as you can see here, with the same architecture, I'm not getting a great performance. Like if if I want to um, compare the architecture where there is no hidden layer, I'm already getting 93, 91% performance. But here I'm only getting a 40% accuracy. Why? Because a lot more parameters. It's a color image. It's much more complicated. The features are more complicated to extract. So, and ANN is obviously struggling. Again, if I add one hidden layer, then the training is also very not very fast actually, not as fast as it was with MNIST. So one exercise that you can actually do is you can compare these two notebooks side by side. It will help you understand the scale of operation, right? Simple images, 28 by 28, just not even grayscale. They are actually binary images, not even grayscale, right? So dealing with that is one issue, but dealing with color images, and these images are again not too big. They are like 32 by 32, very small image. If visually, if you look at it, even you can't really identify if it's a car or a truck sometimes. It's that low resolution, right? So even with that, you can understand the complexity of the task, the resource requirement and all that. So imagine that you are running like the example that we discussed yesterday in real time. There is a network which is actually picking driver signals when a driver is distracted. So one way to approach that is basically have a data set where you have different types of distracted driving. So you have a frame where somebody is looking at a phone. You have a frame where somebody is looking somewhere else. You have a frame where somebody is looking at their co-passenger and talking to them, and then you have a set of label data set where the driver is actually the hands are at 10 to position or whatever, and the eyes are straight, right? So we have a set of labeled images and a set of not labeled images, and CNN classifier is probably sitting in the background classifying the frames in real time, right? Now imagine what is the scale of this operation. The image has to be high resolution, right? So you really can't work with 32 by 32. It has to be some really big image. The feed, the number of frames that comes in every second. Obviously, you don't have to process every frame. Like if a video is basically 60 FPS, 30 FPS, 20 FPS, whatever, right? So you really don't have to process every frame. So you can sample it. You can say like I'm going to sample every 120 frames and I'm going to take the image from there, right? And the CNN, the network which is sitting in the background should classify it immediately and it should give a feedback. It should give an alert or a red light or something should alert the driver to focus back on the road. So it has to be very quick. The latency should be very small between the detection and the result and the implementation. The latency should be really really small, right? So big high resolution images happening in real time, lot of feeds. So you can imagine the scale of operation. Using today's exercise, we understood two things. Firstly, building a model is one part of the game. You can build a model with small images, but working it in scale is going to be really difficult. And that's where the comparison between the CIFAR dataset and the MNIST dataset will really help you. They follow exactly the same flow, but you can see how something that worked with one database might not actually work with the CIFAR dataset and the scale of the operation. You can build a model. You can build a model with 98.99% accuracy, but implementing the model in real time is actually much more challenging than just creating the model. That is part of probably some other module. But as far as the neural networks are concerned, one answer neural networks are not like one size fits all kind of a thing, right? And the three notebooks that we saw today, I think that will help you understand that. Any questions?
Professor, this file is accessible somewhere, the CFR file?
Yes, I'll upload it.
Yeah.
Once it runs fully on my system,
Yeah.
I'll make sure that there are no errors or anything, and I'll upload it.
Thanks, Professor.
Okay.
Yeah, Professor, I have been able to run the second file now.
Great. Okay.
Yeah.
Nice.
Thank you. Yeah.
Thank you.
And our final session, Professor, on 28th for presentation. It will be the same duration and the same time slot, right?
Correct. Yes.
Okay.
All right. So there are no
Professor,
questions. Yeah. Go ahead.
Professor, this is Vijay again.
Yeah.
Yeah, I got the confirmation from my group members saying they are all in. So I think you might need to align a project for us, please.
They are in the sense none of them are allotted any.
Correct. Yeah, they haven't got any project.
Sure. Please
Yeah.
shoot an email to my to me. I'll give my email in the box.
Okay, sir.